All right. We will start chapter 3 now, which is Introduction to Physical Layer. As always, the comments are open. I mean, if there is any mistake I made or anything that you want to correct, or if you want to elaborate more on something, or etc., mention the minute and the second, and do whatever you want. And as always, slides credit goes for the KFUPM University, so it won't be shared. The outline is data and signals, periodic analog signal, digital signals, and transmission impairment. Production physical layer is the only layer that deals with the physical connectivity of two different stations. The layer defines the hardware, equipment, cabling, wiring, and frequencies, pulses, used to represent binary signals, and so on, etc. The physical layer provided services to the data link layer. Data link layer hands over frames to the physical layer, as we know. Physical layer converts them to signals, which represent binary data. The binary data is then sent over the wired or wireless media. This figure, we will see it with each layer. Here, let's give you just an example. Take a look at it. Analog and digital data. Data can be analog or digital. We mean by analog data refers to the information that's continuous. Digital data refers to the information that is discrete. By continuous, we mean this clock, like you can see the minutes, the hours, and minutes, and the seconds. By the digital, we mean the electronic clock. You can see the hours and the minutes, but you cannot see the seconds. And here he is explaining this here, the digital clock and the analog clock. Okay, the concept that you can, one of is continuous, the other is discrete. Okay. Like the data they represent, signals can be either analog or digital. Analog signal has infinitely many levels of intensity over the period of time. Okay, you can see it here. And digital signals, on the other hand, have limited number of defined value. So it's either +1, it's either 0, or +1 or minus. So it's either plus, 0, or minus. Okay, unlike the analog data, analog signal have infinitely many level of intensity. Okay. Periodic and non-periodic. Both analog and digital signals can take one of the two forms, periodic and non-periodic. Periodic means it's like continuously repeated in the same way. Non-periodic, it's not repeating in the same way. It's unpredictable, you can say. The periodic signals complete the pattern within a measurable time frame called a period, and repeats that pattern over and over. So it's predictable. It's we can repeat the same signal over a measurable time. Subsequent identical, the completion of one full pattern is called the cycle. Non-periodic, on the other hand, signals changes without a pattern, so you cannot predict it. You can't have something that is constant and repeat over time. So, but usually in data communication, we use periodic analog signals and non-periodic for the digital signals. So it's a common practice. We use the periodic with analog signals, and the non-periodic with the digital signal. Periodic analog signals classified as simple and composed. Simple, which means only a single wave, but composed, which means more than one waves. Simple periodic analog signals, sine wave cannot be decomposed because it's simple wave, it's only one wave. Unlike the composed, it can be decomposed because it consists of many, more than one sine wave. The sine wave is the most fundamental form of periodic analog signal. When we visualize it, it changes over a course of the cycle. Is smooth and consistent and continuous. Okay, each cycle consists of a single arc above the axis, followed by the single arc below the axis. As you can see, this is above the axis, then below the axis, then above, then below, then above, then below, and so on. A sine wave is comprehensively divided by its amplitude, frequency, and phase. The phase is the starting point relatively to the distance 0. The frequency you can say the starting point and the other starting point. So this one frequency, 1 hertz, okay, and from here to here another hertz. No, from here actually to here another hertz, and so on. The amplitude is the length from the axis to the top of the sine wave, like this, from either top or the bottom, okay. The amplitude, as we said, this is the amplitude, peak amplitude. Here is the low peak amplitude, and here is the high peak amplitude. So the phase, as I said, with the relative time 0. So just describe the position, you can say, of the wave. So if you have like here, for example, it starts from 0, so it's a normal sine wave starting from here. What if it's starting from the top? It will be half of the period, or 1/4 of the period. Then here it will be a half of the period if it starts from the below of the x-axis. But if it starts from the above the x-axis, it's the normal case. If it starts above the x-axis by 1 or more, it will be 1/4 of the time period, and so on. So here you can say there is some rules like the frequency equal 1 over period, and also the period equal 1 over frequency, as you know. Here you can divide the sine wave. Here it will be 1 over 1/4. It's hard to write. What about app? 1/4, and here it will be 1/2 of the period, okay, and here it will be 3/4 of the period, and here it will be 1. So it will be here the full period. It ends at here, okay. So the first one is 0 degree. Here you have 90 degree, the second position. The third position we have 180 degree. An example, it says a sine wave offset is 1/6 with respect to time 0. What is the phase in the degree in radian? Okay, you just take the offset and multiply it by 360, the standard number, okay. And then in order to convert from the degree to radian, you will multiply by 2 pi over 360. Then you will get the answer in radian. Yes, okay. So no, that's complete. Okay, that's it. So you just take the offset and multiply it by 360. Here, the concept of the frequency, as I said, you will count the starting point and the other starting point. It will consider it as 1 hertz. So you will have another starting point here and another starting point here. This is the second hertz. One here, the third hertz. Whenever it's continuous one period, it will consider as 1 hertz. So here in 1 second, we have 12 hertz. If you count them all, you will see that you have at the end 12 hertz. So the period will be 1/12 seconds, and the frequency will be 12 hertz. Okay. Here with the smaller frequency, so the frequency is smaller. No, not the frequency is smaller, actually. Single wave with frequency, yeah, the frequency is smaller here. So we will have 1 here and here, not here, here 2, then 3, then 4. I forget how to count actually. But yeah, first, this is the first, it should be the second, then the third from here to here, then the fourth from here to here, then fifth here, and maybe sixth here. Okay, I hope it's clear. So here the period, which is the T1/6, and the frequency is 6 hertz in 1 second. The wavelength is another characteristic of a single signal traveling through a transmission medium. Wavelength binds the frequency of a simple sine wave to the propagation speed to the medium. So you have the rule here: wavelength equal propagation speed multiplied by the period. Okay. Time and frequency domain. We have two ways to represent the sine wave. So either it's time domain or it's the frequency domain. If it's time domain, you will see it as we used to see it. You have the peak as 5 volt, and you have the normal visualization for the sine wave. But if you have the frequency with the amplitude, then you will just represent this sine wave with the single line, which this 6 represent that it's 6 hertz actually, and the amplitude is 5, so it will stay as 5. So it decided the amplitude decides the how long this line will be. Okay, how long this line will be, and the frequency decide where it should, like if it's 9 hertz, it will be here, and it will go like here till the 5 amplitude, the peak value. So just two ways to represent the sine wave: either the frequency domain or the time domain. Time domain and frequency domain of 3 sines. Like here you have here the first sine, which got nothing, then the second sine, then the third sine. This is when representing it with time domain. Here, when representing it with frequency domain, you will take the frequency of the first one, it's 0, but the amplitude of it is 15. You will make it as 15, the length of it. Then the 8, the amplitude of the 8 will be 10. So you will pick it, the frequency is 8 and the amplitude is 10. Okay. Then you will have 16 and the amplitude of it is 5. So that's it for the frequency domain and the time domain concept. Composite signals, as we said, it's more than one sine wave. So far we have focused on the simple sine wave. Simple sine waves have many applications in daily life. We can send a single sine wave to carry electric. He said here, like to example, to explain that we can use sine wave to carry energy, and we can use it also to report a danger or something. The composite periodic signal, which means that they consist of two signals. There's the first signal and the second signal, which is in blue. Here, the combustion of the composite periodic signals in the frequency domain. Here it's represented in time domain. He asks you, he give you the frequency as the f, then multiplied by 3, then multiplied by 9. So just represent it in the frequency domain. It will look something like this. With the amplitude is not given, so just by the common sense try to make sense of it. Okay. So that's it with the decombustion of the composite periodic signals. So now with the second part, what we have in the second part, we took this and this and this. Yes. The time and frequency domains of non-periodic. Now we are non-periodic signals. So in time domain, it will look something like this. Okay. But in the frequency domain, it will look something like this. This is when it comes to non-periodic. So it's unexpected. It have no pattern and so on. To look something like this. Okay. When representing in frequency domain, you will have the frequency that you guess, then you will fill in the whole thing below the line. And the time domain, you can see it like you cannot predict it, it has no pattern, and so on. The bandwidth, the range between the frequencies contained in a composite signal. So only in the composite signal, the bandwidth concept can be applied. So in the simple wave non-composite signals, you can't apply the concept of the bandwidth. The bandwidth normally is the difference between the two numbers, which is usually the highest and the lowest numbers. So for example, if a composite signals frequencies from 1000 to 5000, the bandwidth will be the subtraction 5000 from 1000, and the answer will be 4000. You can see from here we have a composite signals. This concept only apply with the composite signals, okay? Not the simple signals. So you will subtract the highest frequency that you have with the lowest frequency that you have. This will give you the bandwidth, okay? This will give you the bandwidth. So here in this case, it's 4,000. Also here in non-periodic signals, also take the highest and the lowest, subtract them from each other, you will get the bandwidth. Here's another example. It says that you have 900 and the amplitude is 10. And these are the frequencies. So just write them 100, 300, 500, 700, 900. Okay. And just the amplitude also, it's 10. So it's here, it's this represented in frequency domain. Okay. So you will write them, just represent them as a figure. Then subtract the highest frequency with the lowest frequency, and you will get the 800. Okay. Same thing here. It tells you that to start from the bandwidth is 20. He gave you already the bandwidth, and he tells you that the maximum number is 60. So guess the minimum number. It's of course it will be 40. So that if I subtract 60 from 40, it will give me 20. Okay. Same here, but it's non-periodic composite signals. The bandwidth is 200. So it give you already the bandwidth. It give you the other bandwidth, and it's tell you the amplitude of it. So the amplitude of 140 is 20. All right. And it tells you already that the have an amplitude of 0, the extreme frequency, which means the first one and the last one, which mean here, they all have amplitude of 0, which mean on the x-axis. Now, just by the common sense, you will know, because this is 200, the bandwidth. So of course, the highest number will be 240 and the lowest number will be 40. So that when I subtract 240 from 40, I will get the 200, which is the given bandwidth. Okay. Here we have the digital signal. What we have with this concept, yes. In addition, represented by the digital signals, which is usually the bits 1 or 0, which mean 1 we have positive voltage, 0 we have nothing or 0 voltage. The digital signal can have more than 2 levels. Okay, we'll see them now. In this case, we can send more than 1 bit for each level. So you must understand this. Like here it says, in the digital signals, we deal with the bit rates, which mean how many bits are traveling in 1 second. Here in this case, it's 8. How do you know? By counting these: 1, 2, 3, 4, 5, 6, 7, 8. Okay. You will know the number of bits per second, because all of this graph in 1 second. Okay. With 2 levels. Here we represent, like, we have only 2 levels. The 1 when it's positive, the 0 when it's we have nothing. The 0 will be on the x-axis, the 1 will be above the x-axis, and so on for the rest of it. But what if we have more bits in 1 second? Like here, for example, we have 16 bits in 1 second. How do you know the number of bits? We count each one of these as a double. So at the end, you will have 16. So here, 2, 2, 2, 2, 2. So sum them all, you will get the 16. So that you know there is 16 bits per second in 1 second. Okay. But here we have 4 levels. So just you have you must know the binary representation for the 0, 0. So the 0, 0, which means the level 1. Level 2 will be 0, 1. Level 3 will be 1, 0. Level 4 will be 1, 1. So let's say here you have 1, 1, it will be in level 4. Then you have 1, 0, so it will be in level 3, you can see. Then you will have 0, 1, which is level 2, go down. Then level 1, of course, when you have 0, 0, like here, for example, and so on. So try to understand how to count the number of bits per second and how to draw the lines here, okay? Bit rate, of course, because we don't have it's non-periodic and digital signals, so we can't deal with the frequencies. The alternative thing of frequencies is the bit rate and the digital signals. The bit rate is the number of bits in 1 second, as we said. Same example. Here, just give you an example. If you have 100 pages, what is the bit rate? So he's assume I have 100 pages, 24 line on average. He just assume it, and 80 character for each for each line. So I will multiply it by 8 at the end because I assume that it requires the one character, it requires 8 bits. So multiply them all, you will get the bits per seconds or the bit rate. The bit length is the equivalent of the wavelength, so it will have a law as the wavelength. The law of the bit length is the propagation speed multiplied by the bit duration. Okay, and here there is nothing. Okay. Transmission impairment. The imperfection causes signal impairment. Okay. Transmission impairment, you can say the things that affect the wave that make it change in its phase or representation and so on. So it gives wrong information and so on. This means that the decision at the beginning of the is not the same as at the end. So there is something happened that changed the phase of or the way the wave it looks. Okay, what is sent is not what is received. Okay, simple as that. So we have three type of impairment causes: attenuation, distortion, and noise. We will understand each one of them now in details. Attenuation means a loss of energy. When a signal, simple or composite, travel through a medium, it loses some energy because it's resisting for the medium. That is why a wire carrying electrical signals get warm. Okay. Some of the electrical energy is converted to heat, as we know. So in order to solve this problem, we add amplifiers in the middle of the transmission medium in order to make like this was the original signal. Then it became like this because of the transmission medium. So the amplifier its job is to make it look at after amplified, it will look like the original phase, and then it will get to the point 3 where it's the receiver side until he will see he will receive the wave as it was being sent at the beginning. So the solution for the attenuation is the amplifier. Second type of the causes of impairment is the distortion, mean the singular change from its form or shape. Okay, distortion can occur in a composite single made of different frequencies. Each single component has its own propagation speed and medium, therefore its own delay. So the concept here is with the delay. Decrease in delay may create a difference in phase. So here the signals are being sent, okay, normally. But when they reach this is changing. So this is okay. The first one is okay. The second one is changing. Also the third one is changing. Okay. So the result will be different than the one was that was being sent because of this because each one of them has different propagation speed, so each one of them will send the wave in different time, not all of them at the same time, uh, which will cause delay. So when they reach to the receiver, they will have different phase or shape. Okay. The noise the noise is another cause of impairment. Several the causes of noise, you can say thermal, induced noise, and crosstalk. We mean by thermal noise is the random motion of electronics in the wire that causes heat, of course, which create an extra signal not originally sent by the transmission. Induced noise, you can say, comes from the sources such as motors. Crosstalk, you mean like when there is another wire affecting a wire. So you have this wire and this wire, it's beside it, so they both will affect each other. So you can say at the point when this is what you want to transmit, the noise will cause uh, this noise will cause the original wave to be changed, and the receiver will receive something different. So the causes of noise is this three: thermal noise, induced noise, and crosstalk. Okay. Okay, and I guess that's it for chapter 3.